So next up is beta emission. And in beta emission, zero over minus one beta is produced. And like we mentioned earlier, beta particles are just like electrons, but they're not from the electron cloud. So the electron cloud electrons, those are chemical reaction electrons. Nuclear reactions don't involve any electron cloud stuff directly. So this electron can be produced in the nucleus. And so these happen in situations where there are too many neutrons in the nucleus for it to be stable. There's a preferred kind of ratio for neutrons to protons. We'll talk about that eventually. But that neutron to proton ratio, when it gets out of whack, that's what results in these nuclear processes that result in stabilizing the nuclei. So in a nucleus where there are too many neutrons, a neutron, which is 1 over 0 and a small n for a neutron, mass of 1, no charge, converts itself into a 1 over 1 proton. That's a small p for proton, not big P for phosphorus. So a neutron converts itself into a proton. Well, to balance this out, the masses are okay, but we've created a charge where there wasn't one. So to balance that out, we get an electron, and we call these particular electrons beta particles. So this allows the masses to balance out, 1 and 1 on both sides, 0 on the left, 1 minus 1 is 0 on the right. So this beta particle gets shot out of the nucleus at nearly the speed of light because it's not allowed to be there. It has to leave. Even though it's really attracted to the nucleus because of all the protons that are there, it has to go. So these beta particles are what get shot out of the nucleus. They're identical to an electron, but they're not from the electron cloud. So balancing these reactions doesn't work that much differently than for the alpha particles. It's the same process, but it's a little bit trickier because we're subtracting minus ones. Okay? We'll see that on the way through our examples here. So when we start to balance these, the first one is bismuth 212. So bismuth 212, it's got a charge number or atomic number of 83. Produces 0 over minus 1 beta plus the daughter atom. Now we're still doing the same math we did on the alpha particles, but it's a little bit more complicated now because of the minus charge over here. So the masses are easy, right? 212 over here, no mass on the beta, so the daughter atom is still 212. Now when we do the charge numbers, we just have to be careful. 83 minus a minus 1 is not 82. 83 minus a minus 1 is 84. That's the part you got to be careful with. Find box 84 on the periodic table. It's PO for polonium. So again, make sure that you remember to slow down, take your time on what to do there. Or a couple more examples of this process. Now we've got, the next one up is radium 228. Radium is box 88. So its atomic number is 88. Produces 0 over minus 1 beta plus, now the mass number isn't going to change, 228 minus 0, still 228. Goes from 88 minus a minus 1, which means 89. Make sure you get 89 on that. Box number 89 is AC for actinium. And that's your daughter atom. One more example. Thallium 208. TL for thallium. Thallium is in box 81. Produces 0 over minus 1 beta plus, now our daughter atom will have the same mass, 208, 81 minus a minus 1 means 82, and that's Pb. So lead is the product there. So this is how all of the beta decay equations balance. But you got to remember what to do with that -1 there as you balance the equation. We'll come back, we'll look at the next one, which is positron emission.